Hello everyone, welcome to Acing Academy's YouTube channel. My name is Arjun Chabra. I'm a faculty at Acing Academy and Ace Online platform. So in this today's session, we'll be covering up what are the ISRO PYQs for design of steel structures. And students must focus on the fact that uh, ISRO is nearby now, ISRO examination is nearby. Their prime focus should be, understanding what kind of previous year questions they have been asking about, and also the level of questions are not that high as gate level. Now, they are very straightforward questions, just like your AEJE questions or one marker of gate examination. So if you are a student who has been also preparing for some state level examinations, it would be similar to that level only. Now, as far as your subjects are concerned, the subject weightage I had initially told you in a video which I made on the same channel itself. You can just check it out once. On that particular video, I shared about the fact that, what have been the weightages of various subjects of civil engineering for ISRO examination. Now, as far as this particular subject is concerned, design of steel structures is concerned, not many questions have been asked previously, and you can expect still a less number of questions only, right? Now, this is a hard fact that ISRO examination and also GATE examination don't tend to ask that many questions in design of steel structures, right? So you have to keep this in mind. Now, as far as the subject is concerned, what are the prime focus? What should be the prime focus in this particular subject? Now, the prime focus should be primarily your basic concepts and codal provisions. That's it, right? Now, basic concepts, you will see that, with respect to limit state method, working stress method, ultimate load method, such questions can be focused. And apart from that, codal provisions from connections, right? Connections, that is your rivets. You can't ignore rivets chapter because in rivets, you will see a lot of questions from rivets in state level AEJE examinations as well. So therefore, you can't ignore the rivets topic. So rivets is not very common for gate examination, if I say, right? So rivets is required to be focused, right? The codal provisions are approximately same as that of bolts only, but still there are some differences. So rivets, bolts and welds, all of them shall be considered for your revision series. And moreover, you need to also focus on members part, right? So previously it has been witnessed that a lot of questions have been asked from compression members topic. Now, tension members, not many questions have been asked. Beams, a very limited number of questions have been asked. So compression members have been the topic in ISRO examination specifically, in which good amount of questions have been asked, right? So you don't need to focus too much on later parts, later subjects like you can say base plates. Not many questions have been asked from base plates, right? A couple of questions have been asked from the chapter trusses, industrial roof trusses. You can also expect that IS 875 part 1 can be considered for our consideration, right? In terms of wind loading, questions can be asked. In terms of live loading over industrial roof trusses, it can be asked. So these particular topics have to be focused in terms of industrial roof trusses. Apart from that, let's move forward with our question series, and let's see what kind of questions have been asked in ISRO PYQs. We can also refer various codal provisions as well along the side of your ISRO series, right? Now, so let's see first question over here. So over here, what they are saying is steel contains carbon approximately. So steel approximately contains 0.05 to 1.75% of carbon content. If I talk about specifically structural steel, right? When we generally talk about structural steel, the steel which is used for the structures, in that we generally vary the carbon content from 0.05 to 1.75% or 1.7%. So on the basis of carbon, the steel is classified into low carbon steel, medium carbon steel, and high carbon steel. So different books have different ranges, right? Because most of the books are, you know, made out of research papers, and a lot of research has been dealt into making such books or publishing those books. But when you see the major books like S.K. Duggal and N. Subramanian, if you combine them, you would see that low carbon steel will be ranging from 0.1 to 0.25%. Here, this will be from 0.25 to 0.6%, and then this will be 0.6 to 1.7%, 1.1%, right? So close to that, you will see the range. So these are not fixed values as per the code, but shall be considered. Now, this is your carbon steel classification. And what are the effects of carbon? As we know that carbon content tends to increase the rigidity of our steel, right? It increases the hardness of our steel. So if you increase the carbon content, so you would see that rigidity will increase, right? Apart from that, hardness would increase, resistivity to abrasion will increase. If you lower down the carbon content, the rigidity will reduce, the rigidity reduces, and you can say ductility increases if carbon content is low. If ductility increases, so you can also expect that toughness increases. If carbon content increases over here, in that particular case, the ductility tends to become on a lower side. So when we say that rigidity, hardness increases, so we can also expect when carbon content is increasing. So in that case, ultimate strength also increases. When carbon content reduces, the ultimate strength tends to reduce. So we have to keep all of these points in mind in respect of carbon content. Now, carbon content is one of the most influential constituents of our structural steel. In structural steel, you will find, in standard structural steel specifically, if you will say, you'll find that carbon content, standard structural steel is your mild steel, right? So Fe 410. In that particular case, carbon content is 0.23% as per IS 2062, right? So these points in respect of that you need to consider. So here this will be under the category of low carbon steel. Right? So you'll find good ductility in this if you want to increase the strength of this, or if you want to increase the grade, so you'll have to increase the carbon content. So carbon content comes out to be the most influential of the all, though 98%, more than around 98% is iron only in steel, right? But carbon tends to be the most influential one because this carbon actually occupies void spaces in the molecular structure, and it tends to influence the rigidity a lot. So the space which is occupied by the carbon is amongst the void spaces, so it tends to increase the rigidity in that case, right? Now these are some points, extra points for you all on the basis of carbon content. Next one, here they are saying rolled steel equal and unequal sections are designated as ISA, ISA followed by. So obviously your angles as per Indian standards, they are either equal angle sections or unequal angle sections, right? Now in equal angle sections, both the legs tend to have same length, and in unequal angle sections, the length is different, right? Now they are also specified with respect to their thickness. So in general, if you'll say that I have taken an Indian standard angle or equal angle section with thickness of 75 mm and leg length is 100. So it will be classified as ISA 100 by 100 by uh, thickness as 8 mm, let's say. Right. So here, after it has been designated with its leg lengths, it will be signified by the thickness. And this thickness will be in mm, right? So leg and thickness of the legs is generally considered for Indian standard rolled steel sections in their designations, right? And similar ways, if you'll see that I section, channel section, right? These two are one of the most important cross sections. You would see them being designated by their total depth and dead weights, right? Um, Apart from that, let's see our next question. Over here, they are saying a particular grade of steel is termed as Fe500. So Fe500 is generally in respect of the reinforcement, RCC reinforcement. So over here, Fy, I would consider that it is represented as yield stress. So if the question would have specifically justified that they are talking about reinforcement or structural steel, in both ways, you tend to designate the number in the designation as different. So if we talk about reinforcement, right, in RCC, reinforcement concrete, so in that case, it will be yield stress, right? And generally, you won't find Fe500 specifically. So Fe410, if you say that it is to be considered for structural steel, here 410 represents ultimate stress. Here 410 represents ultimate stress. So you need to keep this in mind. The unit weight of rolled structural mild steel is about in grams centimeter cube. So yeah, it is 7.85. Apart from that, next question, here they are saying junction between the flange and web of the beam is known as, okay. So if you consider a rolled I section like this, over here this junction, it is in regard of increasing the bearing strength. So you generally do not provide sharp edges or sharp corners in the manufacturing process. You tend to round them up. This rounding tends to help with the bearing stress from concentrated loads. It is called as a fillet, right? Or it helps to prevent stress concentrations also. So it is option C. Next, a very simple question. Distance between the centers of the adjacent rivets in the same row is called as. So in the same row, distance between. So if you are measuring parallel to the applied load, it will be pitch, and perpendicular to applied load, it will be gauge. So in one row, it will be pitch, right? And in one bolt line, it will be one gauge length. Apart from that, let's see this question over here. They are saying when two plates are placed end to end, are joined by two cover plates, it will be called as a double cover butt joint. It's quite easy. So double cover butt joint, you tend to see that the plates are connected edge to edge, right? So over here, there is no lapping in the main plates, which is observed. So you would see, and there is some space, you know, there is no connectivity over here between the two plates. You can expect that there is very minor spacing in between it. Now, apart from that, these are what? Cover plates. Now, you have to keep this in mind that the thickness of the main plates should be, should not be in such a way that the thickness of cover plates is varying. Right? The thickness of the cover plates should be sufficient enough that it should be able to take up the load. So generally it is, in this particular case, 5 by 8 times the thickness of the main plates. It should be there. During the design, we generally consider it. Apart from that, let's move forward. Out of all the available roll seal sections, the most commonly used section as a beam is obviously I section. I section is also called as Indian standard. So I section in your steel table is specifically justified as a beam section only, right? And I section is one of the best sections to be acting as a flexural member, right? That is a member which is subjected to bending. So as a beam section, I section is one of the best cross sections because for the same cross section area, it tends to give a very high, a good amount of increase in section modulus is observed. Because of that, the moment resisting capacity of an I section for same cross section area tends to be higher. So the efficiency of an I section shape in respect of taking up bending stresses is very good and it is very efficient. Apart from that, next question, the distance from the center of one rivet to the center of another rivet in one row is called as pitch, as discussed previously. So question, you can see the questions they are repeating again and again. There are multiple other questions also which were repeated. I may have removed the slides for them, but repeated questions tend to had different options. Here you can see they have provided different options than the previous same questions they had asked. So this has been done 2 or 3 times in ISRO previous years. Apart from that, you can see rivets are specified by rivets are specified generally by their shank diameter. So as we know, in rivets there are 2 parts. There is one head of the rivet and this is the shank portion of the rivet. Right? This is your shank portion of the rivet. And if I say that I am taking M16 rivet, so over here 16 signifies the diameter of the shank portion. Diameter of the shank portion is being justified right over here. So over here, and similarly, the bolts are also justified by or specified by the diameter of the plain shank portion. So as we know that in case of bolts, we see that there is a plain shank portion and there is a threaded shank portion. So over here, threaded shank portion is lesser as compared to the plain shank portion. And over here, this bolt will also be justified by the or specified by the diameter of the plain shank portion. And also keep it in mind that the area in respect of this threaded portion, let's say it is ANS, that is net area of the bolt, and area in respect of this plain shank diameter, it is, let's say, signified as AS. So AS is equal to 0.78 times, sorry, ANS is equal to 0.78 times AS. ANS is equal to 0.78 times AS, right? So it is 22% lesser. Over here, shank diameter, option B. Next is, in the design of connections in steel structures, the distance between the center of any two adjacent fasteners shall not exceed. So it shall not exceed 32 mm or 300 mm, right? In any case, it cannot be less than that, right? And specifically, if they had mentioned that what kind of force is there in tension force, when tension force is there in case of pitch, this shall be considered 16T or 200 mm and 12T or 200 mm in case of compression, right? These points are required to be considered. 100 mm plus 4T, I guess it is edge distance, right? So the average shear stress for the structural steel rolled beams is calculated by dividing the shear forces at the cross section by. So over here, the average shear stress of the structural steel rolled steel beams is calculated by dividing the shear force. So average shear stress will be equal to this. So over here, this area is the web area. If you consider a rolled steel section, you would consider this shaded portion as your web area. So shear area is equal to D into TW. Similar thing has to be considered for rolled channel sections as well. In rolled channel sections, we generally again tend to consider the web area, right? So web area tends to take up the shear stress. Now, the thing which is not mentioned in the question is that the force applied is perpendicular to the major axis, right? That means we are talking about major axis bending in this particular case. Major axis bending is there. Now, if there would have been minor axis bending in that particular case, the load should be taken by the unshaded portion of the flange area, right? Unshaded portion of the flange area, 2 into BF into TF. Not the unshaded portion entirely, this portion will also be included, right? In case the load had been applied like this and the bending would have been along the minor axis, right? So this is for minor axis bending. And this is for major axis bending. So all of these points have to be considered in terms of solving the question, but here option C, gross section area of the web, shall be the correct answer, because in most of the cases when nothing is mentioned in the question, you have to assume that major axis bending is the concept they are talking about. Next, here let's see the maximum axial load, which is just sufficient to keep a column in a small deflected shape, is called as crippling, buckling, critical, all of the above. Simple, right? So it is not a conceptual question, it is just like your basic general knowledge question which has been made, right? A steel member that is primarily loaded in the tension is called as, it's a tie member. Strut is a tie member is a tension member in a truss, and strut is a compression member in a truss. So I'll write it over here. This is tension member in a truss, and this is compression member in a truss, right? Next, the sectional area of tension member is the tension, what is this? They are saying, yeah, net sectional area of the tension member is equal to its gross area minus the area of the holes, right? So in the net sectional area, we generally tend to subtract the area of the holes. It has to be subtracted, then only you will get the tensile strength. If we are talking about working stress method, in that particular case, we generally consider only the net area of the cross section, and in case of limit state method, gross area will also be considered in the cross section yielding criteria, and net area is also considered in the net section rupture criteria, and both are individually considered, not for the entire cross section but for the cracked cross section or the yielding cross section in the block shear strength as well, right? So limit state method is more tedious as compared to working stress method in terms of formulas I am talking about. In tension members, there is only one formula which we generally consider, sigma AT multiplied by the net area, and over here in limit state method there are three different formulas, three different types of formulas which we need to consider for a particular section in a particular case. Then slenderness ratio of a compression member is defined as its effective length divided by the radius of gyration. Is very simple, right? Apart from that, here they are saying the thickness of the single flat lacing should not be less than. So single flat lacing somewhat look like this. So in the figure, as you can see, this is single lacing which is going on, and this is what double lacing which is going on. The thickness in this particular case shall not be less than 1/40 times the effective length of the rivet. Now the effective length generally can be considered as inner end, distance between the inner end of the rivets also when single bolt is there. It can be considered that. So in this particular case, 1/40 times, 1/40th time length of the inner end of the rivets, and 1/60th of the effective length of the lacing shall be considered in the case of double lacing system. So here 1/60th times effective length, and here 1/40th time effective length of a single lacing. Here next, a strut is a structural member subjected to. Strut is a structural member subjected to compression in direction parallel to its longitudinal axis. So what is the perfect definition of a compression member? So in a compression member, if you'll say that this is your longitudinal axis which is passing through the centroidal axis also coinciding with that, the load line also coincides with the longitudinal axis, it will be a purely compressive member. In this particular case, option C will be the correct answer. After that, what are they saying? Which of the following is the best compression member sections? So best compression member section will be a tubular section, right? Again, tubular section will not have any weak axis. So if bending want to happen about any of the axes which is passing through the CG of the cross section, here there is no weak axis, and therefore it is one of the best cross sections of taking compression as well as torsion also, because of higher polar moment of inertia for the same cross section area you can attain as compared to a solid circular section. Solid circular section is also good, but this will produce higher strength for same cross section area. I am repeating, and for the same cross section area, tubular section will be having much better performance. Apart from that, here they are saying the effective buckling length of a steel angle connected by double rivets is. So over here, specifically, they are talking about the buckling effective length in terms of the criteria of double, right? So they are saying double rivets. They must be talking about the struts, right? So generally, such codal provision is given for struts, continuous struts and discontinuous struts. In this particular table, you can take a screenshot of this if you want, that it will be helpful for your future as well for revision. So over here, if there is a single angle connected with more than one bolt or welded, in that particular case, in the plane of the gusset. So if this is your connection, if the buckling is happening like this, in the plane of gusset, the angle you are obtaining, then in that particular case, it is 0.85 times L over here, quite visible from the figure, table itself. Now, what is out of plane buckling or perpendicular to the gusset? So you can imagine the gusset buckling outside of the plate. So that can also be considered over here. So this is 0.85 times L. So this is from the strut topic, right? This is not your regular effective length consideration. Now after that, here they are saying a 40 centimeter diameter circular timber column is 4 meter long. The slenderness ratio is, so they are saying 40 centimeter diameter timber column. So in that particular case, radius of gyration for a circular section is d by 4. So here diameter is 40 centimeters divided by 4. This will be equal to 10 centimeters, right? Apart from that, slenderness ratio, it is equal to the effective length divided by radius of gyration, considering effective length in centimeters. So this will be 400 centimeters divided by 400 centimeters divided by 10 centimeters, right? So yeah, d by 4, diameter I've taken 40 by 4, 10 centimeters, length is 400 centimeters, and then divide by 10, this will be equal to 40 centimeter. So here it is 40, option D. Next they are saying the two steel long columns, P of length L, Q of length twice of L, it has the same cross section area, the strength characteristics as well as the end conditions, the ratio of the buckling load of the column P to that of column Q, ratio of buckling load of column P to that of column Q. So buckling load, let's say critical buckling load, is inversely proportional to the square of the effective length, right? So I would say that PR divided by, no, we'll write down like this, PP divided by PQ, PP divided by PQ. I'll erase this for better clarity. What is the ratio they are asking? Buckling load of column P divided by Q. It will be equal to effective length of Q divided by effective length of P whole square, right? So over here, the effective length is twice of L. This will become 4 by 1, right? So it will be 4. Option D. Now next is a column splice is used to increase. So how does a column splice look like? So it tends to look like this. So you can see whenever there is some discontinuity, which is to be encountered in case of column sections, maybe due to the lack of availability of the length which is required on the site of the steel section. We need to maintain the continuity. For the maintenance of the continuity, we need to provide column splices. Now, generally there is also a norm which we see that the columns which are there on lower side of the building, they have a higher depth, and as we move forward, move away from the bottom story to the higher stories, in that particular case, you would see that the depth of the cross sections need to be reduced. in that case also, we can provide by filler plates as well as bearing plates, we can provide uh, column splices in that sense, right? So column splices tends to provide continuity of length of the column, right? So column splices are used to increase the length of the column. The permissible stress in bending for steel I-beams for FY 250. So it is for axial compressive stress and for bending compressive stress and bending tensile stress. The permissible stress is 0.67 times Fy. So if you'll consider 0.67 times Fy, it will be 165 Newton per mm square. Now let's see our next question. Over here they are saying the fact that as per IS 800 2007, the maximum allowable vertical deflection due to the combination of dead and live load for purlins supporting elastic cladding. So for elastic claddings, you can see it is spanned by 180. For brittle claddings, it is spanned by elastic cladding spanned by 150, and brittle claddings spanned by 180 you shall consider as per IS 800 2007. So higher value for elastic claddings, lower value for brittle claddings, as you can see, right? So over here, option C will be the correct answer. Next, over here they are saying the self weight of the steel truss in Newton per meter square may be computed by. So yes, so steel truss dead weight is equal to span by 3 plus 5 multiplied by 10 Newton per meter square. Also, sometimes in design, you can also consider it as 10% of the imposed load. Right, 10% of the imposed load can also be considered as the self weight of the roof truss. So that can be considered as option B as the correct answer. Next is the crippling generally occurs at a point where. So crippling generally occurs if you talk about plate girders or beams. The web crippling can occur in the case of concentrated loads. Wherever they have applied concentrated loads, either along the length of the beam or from the bottom of the beam as well. So you will see the crippling can be like this of the web. So in this particular case, what happens is web is trying to fold over the web. The web is trying to fold over the flanges. You can clearly see like this. And then near the supports as well, there is also a possibility. Like this, failure can happen when load is from the bottom, like reactions are there from the bottom side. So yes, concentrated load, when it acts, it tends to produce this kind of failure. Now here they are saying the stiffeners are used in plate girder to reduce the compressive stress. Obviously, you will not provide anything in the structure to reduce something, right? So mostly the strength is supposed to be increased. So to reduce the compressive stress, to reduce the effective stress, to take bearing stress, to avoid the buckling plate, to avoid the shear buckling of the web plate. So mostly you would see that there are two types of stiffness which we generally provide: horizontal stiffness and vertical stiffness. The design of these stiffness is in respect of when we talk about serviceability, there is serviceability criteria entirely, which is given in IS 800 2007, and there is compression flange buckling criteria as well For the transverse stiffness, specifically the vertical stiffness, the provision is there. You can also consider them separately, but I guess for ISRO-like examination, it won't be that much important. Next is the web crippling in a steel structures is on account of. So it is on account of failure of the web under concentrated load. You can see the question has been repeated with the language being changed for the options. So this is the case which has been witnessed in ISRO. I've seen this happening in different subjects as well of civil engineering. Web buckling occurs in a beam due to excessive direct tensile stress in the web, bending tensile stress in the web, torsional shear stress in the web, compressive stress in the web. So web buckling is primarily due to the compressive stress in the web, but this compressive stress in the web, if they would have mentioned not torsional shear stress, right? It is not torsional shear stress. This compressive stress is induced because of the shear stresses only, right? That is why we call it as shear buckling failure. When you consider an element right over here, which is a pure shear element at the neutral axis, in this manner, if you consider. So here what you would witness is the deformation of this element will be somewhat like this. So because of this compression which is induced, the principal compression which is induced, because of this there would be diagonal buckling failure. SF2 is what? Compressive in nature. So you would see diagonal buckling failure over here, and in the cross section it would be visible like this, in this manner, right? So buckling will be somewhat like this in the beam section, but it happens diagonally. So if you'd say that from the front view, if you want to witness, it will happen like this. So option D is the correct answer. Next is the maximum allowable deflection of gantry girders supporting EOT, that is electrically operated overhead cranes of capacity less than 50 tons. So if you'll see this table over here, for MOT cranes, it is spanned by 150. For EOT cranes, the permissible vertical deflection is spanned by 750 up to 50 tons. If it is greater than 50 tons, spanned by 1000. For other moving loads like charging cars, in that case, it will be spanned by 600, and lateral deflection or horizontal deflection shall be 10 mm, right? So for our case, span by 750 shall be considered. So option C is the correct answer. So that's it from your ISRO PYQs. I hope it was helpful for you all. You can see the level of questions which are asked in ISRO examination are very lower. Your preparation should be also in respect of the level of questions only. You should not go beyond the level of any examination. If you want to go exam specific selection, your major focus should be solving as many questions as possible. So this was an attempt of Ace Learning Academy to help you in regard of letting you know that this is the level of questions which are asked if you are unaware about the fact that which type of questions they would be asking. So your preparation right now should be entirely focused on the level of the questions. So whenever you are revising your concepts from your short notes or notes, tend to always think about the level of questions and try to think okay, if they would frame a question from this, what kind of question can be framed? And what is the level of question which can be framed, right? This should be your thought back of the mind. And apart from that, try to solve some assistant engineer previous year questions as well of various states, AEE examinations which are there, or PSU examinations, previous year questions, because similar level of questions have been asked in ISRO also, and it will be asked in the forthcoming examination as well. So thank you for being part of the session. I'll see you in the next one.